Take it away, Claes.
Yeah, I only have 18 slides, so I'll run this fast. Should we pass around some hardware? Yeah, I brought some prototypes. And so, Botani.st, has anyone heard of us? Is anyone into gardening?
Yes.
Good, then you like this. Is anyone into growing stuff that the government probably don't want you to grow? Good. Yeah. And then you might want this too. But don't say that to the government. So my name is Claes Jakobsson. I'm the basically head honcho. So I do most of the stuff except the hardware, because I really suck at electrical engineering. So do not ask me any hard questions, because I will not be able to answer them. I've been doing mostly financial systems my whole life, which is extremely boring. So doing hardware every day puts a smile on my face. When you come in the morning and you say, oh, I have 128 bytes of RAM in this device. This is going to be so much fun today. So let's see some pictures. Oh, that's our prototype of the wireless sensor. In case you're wondering how big these are, they're about 3.5 centimeters square, which is way too big. And the new one will be about 2.8 centimeters square, including battery, solar cell, radio, and all the sensors. So tiny stuff, but can be made even smaller. There's a picture of the wired one. So what we do is we build like a hardware and software platform for growing stuff, mostly plants, but you can, in theory, it's a fairly generalized hardware platform that just happens to be used for gardening. But if you want to run other sensors on it, feel free to do it, because we will be open sourcing most of the stuff, and all the hardware will be fairly open, so you can build your own sensors and actors if you want to do that as well, and you can run virtual devices if you want to connect to your PLC or your irrigation controller or whatever. Let's see some more screenshots, action shots. That's some of my plants. Don't complain, because they look really sad. So let's see, should we skip down? Yeah, so that's the platform. We designed it to be really affordable, which is extremely difficult to do, because apparently stuff costs way too more than you want it to cost. It has to be extremely simple, because our main audience group is like 40, 50-year-old women who might not be that tech savvy. So they have to be able to use it. And being an open source guy, I of course wanted everything to be as open as possible. We also want, it must work offline. So it's, in theory, it's not an Internet of Things product, because we don't use IP, and we do have a cloud service, but we prefer if you run it locally, because the cloud service is more or less just a read-only mirror of the data that you have at home. I've been doing this way too long, for 3 years now. So it's been more of a research project, learning all I can about gardening and how you build sensors cheaply that works in a garden environment. And we're trying to commercialize it now. So if you have some money to throw at me, please do so. I will gladly take it. So I could talk a lot of Botani.st about the architecture and stuff, but that is kind of boring, since this is a hardware meetup, specifically about sensors. So let's talk about the sensor. The standard sensor, where is it? Somewhere there, right? So that's like a 5th generation sensor. The standard sensor that we build is mainly for soil-based cultivation. So there's other ways to grow plants, for example, hydroponics, where you grow it in water. There's an extension of hydroponics called aquaponics, where you have living fish that poo, and then they turn the poo into nutrients, and that the plants get happy. And then there's also aeroponics, where you grow it in air, basically, with like a moist environment. But our sensor is only for soil-based cultivation, and with soil we mean like normal plant soil, but it also works in coconut fiber mixtures, and it works in like sand. It will not work for your orchids, because those you normally grow in what's called bark in Swedish. We have it in a wireless version and a wired version. those ones that I'm passing around is the wired ones. They're much cheaper than the wireless one because we can eliminate the battery and much of the other stuff. So they're mainly for if you have a greenhouse, you have an irrigation, and you have all other kinds of stuff. You're normally fine with having wired sensors. And then you can get away with around between 120 and 150 Swedish kronor for each sensor, which is kind of fine. It measures soil moisture, it measures ambient light, and it measures temperature in both the air and in the soil, because you want to know both of them. We had some challenges during the development. People said, oh, I don't want this to take focus from my plants. So it has to be really, really tiny, which I think we've done. Some of our 2 or 3 competitors, which exist, they're like big and ugly, if you ask me. And you don't want that, you want a small one. It has to survive in a fairly harsh environment, because you don't want to take out the sensor when you water. And if it gets too cold, well, you don't want to have to take them in. In a greenhouse, it's usually fairly humid, so it has to survive in that. And there's some other problems with mechanical, tension when you put them down in the soil as well. It had to be really, really cheap to build, so we had to minimize the BOM, and we had to make it single-sided to lower the manufacturing costs and all kinds of stuff. Too much work went into that. So let's see, that's a picture of oh, it looks crap. That's a picture of like the 5th generation sensor. And we have 2 temp sensors, and we have a microcontroller, which happens to be an AT-Tiny. But the new ones doesn't have AT-Tinys, we switched to ARM. You have this is the soil moisture sensing part. We have, a nice feature, we can daisy chain our sensors. So you can plug in one sensor to another in the daisy chain, and it works. So you don't have this ugly mesh network. We have a LED that we also use as a light sensor, and this one has a voltage reference, but that one is gone because it's not needed any longer. So that's basically the sensor. So how many of you have ever built a soil moisture probe? Good. So how did you build it? Resistance or capacitive? Resistive. Okay. Did it work good?
Yeah. I think that was only
Okay. So basically, when you measure soil moisture, there's 2 basic versions to doing it. Either you measure the resistance of the soil, or you measure the capacitance of the surrounding medium. Building a resistance meter is extremely simple. You just pass a current, and then you measure the voltage on the other side. But it works really crappy, mostly. It can detect, is there water? Is there no water? Is there a little bit of water? But then you start adding nutrients and salts and changing the temperature and changing the soil medium, and then your values go poof. So then you turn into capacitance sensor, where you basically use the medium as a capacitor that you charge really, really, really fast. And the faster you charge it, the less noise it becomes. It utilizes the fact that water has a much bigger dielectric constant than air or soil. I think air is around 1, vacuum is 1, water at 20 degrees is 80, and soil is about 4. So you can use that fact to calculate the more accurate soil moisture. I can't tell you how accurate it is, because we haven't really measured that, but it is fairly accurate during our test. I would say somewhere around in the region of plus minus 5% or less accurate. It happened to be that the response from the sensor is extremely linear, which is very nice. So you don't have to do any complex mathematics to convert it to a percentage. You need to know the temperature of the water surrounding the soil, because it changes the electric constant. When it gets really warm, it gets really low, but normally then your plants will die of other reasons. So the major problems we had is that an oscillator is an expensive part. It turned out it was about 25% of our BOM cost, which is $0.75 US, so you can figure out how much the hardware and that stuff costs in really. The initial one version used an analog comparator for doing the for making the square wave that we put into the capacitor, and then you get you measure the time it takes for it to discharge, and then you put that in the comparator, and you get some PWM signal out that you convert through a low-pass filter to a voltage, something like that. I don't know exactly how it works. But that was a really expensive component, but apparently you can use an XOR for it, which was really nice, because those are dead cheap. So, small trick. Then, of course, there's the problem with water surrounding the components. So you get a short if you don't do any conformant coating, which actually also turned out to be quite expensive. And there's a funny thing, because some of the PCB manufacturers, they said, oh, this PCB is going to work like a sponge and soak up water, and you're going to get shorts within the PCB, because we use 4-layer PCBs, since we have no contact with the medium that we measure. But I've had PCBs in water for several months, and nothing has happened. So I wonder if this is just a happy coincidence that they are very well glued, or not. But I guess we have to do some kind of coating to protect them, since they have to survive for 3 years, and then the warranty is out, as I see it. You also need some kind of mechanical protection. So if you see the one with the box, there's a small plastic over the actual components that go under the in the soil, because there are rocks and stuff in the soil that can otherwise tear off the components, and then it will not work, apparently. Yes, that has happened. So ambient light, we did a lot of tests for how to measure lightning. So I think I had a rig up with 20 different kind of photodiodes and phototransistors and ambient light sensors, ranging from really, really cheap to really, really expensive. And some of them were good, but then we figured out, well, I didn't do anything. My companion who does the electronics, he said, oh, you can use a LED as a sensor. If you light a laser on a red laser on a red diode, it will give you some electricity on the outside. So we did that, and we measured the voltage, and it worked fairly good. But then apparently there's a better way to do it, and that's you charge the LED, but you don't have a ground, and then you put the ground as an output, so it sucks out the energy somehow, and then you measure how long it takes for it to go down to 0. And from that you can figure out if it's dark or if it's light or cloudy or overcast. And it works fairly okay, but it's... Sorry? Oh, if you have any questions, just raise your hand. It is not a lux meter. It's very crude, but it works accurately good for a consumer-grade electronics part for that kind of money, so to say. There are some problems. We don't do any continuous sampling. So if it's very changing clouds, it might be unhappy that it's every time it samples, it happened to be sun, but 75% of the time it's actually cloud. So that we have to solve. I have some ideas how to do it. But since we envision that you normally have more of these sensors running, we can actually take the data and we can group them and use sensor data from other sensors to figure out what to do. So it's, in theory, it's a problem, but in practice, it will probably not be a problem, which is kind of nice. Then, of course, plants, they have leaves, and leaves can cover the sensor. So it is not facing upwards, it's actually facing to either side, because that is normally not where you have leaves. So extremely simple design. The temp we measure using Texas Instrument sensors. Here too we build a lot of rigs with practically every temp sensor there is on the market, and tried which one is gives us the best price performance. and it happened to be that the Texas Instruments LMT87 was a good match, which we will of course switch to another one now, because why not? It has a typical accuracy of plus minus 0.0 degrees Celsius, which is typical. In worst case, it's like plus minus 3 degrees, but you can figure that out during calibration of your sensors and just don't chip them. It has a very wide temperature span from minus 50 to 150 degrees, far more than any of your plants will ever survive. It comes in a really small package and they're very low price. Thermistors exist. We have the MPC 9700 from Microchip. That could work as well. But eventually we settled for this, and there's a good reason why. And then of course we have two. So sense accuracy, how much time do I have? 4 minutes? Oh, that's fine. So they say you get 0.3 degrees accurate sensor, but then there's a lot of stuff in the way transforming that 0.3 to something that we can actually read. And if you do a bit of the maths, they tell you it's 13.6 millivolts for each degree that output that you get. And using a 12-bit ADC at 3.3 volt, which we normally do, that would give us about 0.8 millivolts per step, or our ADC would be accurate to 0.05 degrees. And add that with 0.0 degrees, it works. But if we use a 10-bit ADC, it turns out, well, there's 3.2 millivolts per step, which is roughly 0.23 degrees. And then you add that, and then you suddenly, oh, you have 0.5 degrees accuracy. And then, of course, you also have that you need to know the voltage in order to get an accurate calculation. And the built-in voltage reference in the MCU that we used was really crappy. So it had 10% accuracy. So we had to put in an external voltage reference, which gave us 1% accuracy. So this is actually not what we're giving you. We're saying like plus minus 1 degrees just to be safe. But that is fine, because that is, it's okay for a greenhouse or for your balcony. It's not a scientific instrument. So what are we doing now? Recent changes that are not visible on that, we're switching to ARM all across the line. So Atmel released their, they have this D21, which is used, I think, in one of the latest Arduinos. They took that and they made a much smaller version called the D09, which is basically the same core but less flash and less ROM, which is still like 20 times more than we actually need, but it's as little as we can get, and they're dirt cheap. They're like 4 Swedish crowns each in volume, which is nice. They have a much better ADC. They have a much better voltage reference. They're slightly smaller, so they're 4 times 4 millimeters, and that one is 5 times 5, so we save a bit of PCB space. And the nice thing is, you can actually, they run at 8 megahertz on the internal RC oscillator, and we can use that through the phase lock loop and actually get a 48 megahertz clock out from the chip. And then we can use that clock out and remove the oscillator that was really costly and just use the clock out from the MCU instead. And of course, we get a bit of more noise on the moisture sensor, but that's fine if we save 6 Swedish kronor. We also have a bit of a problem with voltage drop. Since you can daisy chain these, the last sensor in the chain will not get 3.3 volt. It will get, like, if you have 7 or 8 and you have 1 meter cable, I think we measured about 2.8. And then suddenly, some of the temperature sensors that we used, well, they stopped working. Fortunately, why we choose the LMT87 is that they also produce a lot of versions of it with different sensor gains depending on your source voltage, which is nice. Then we could also save 1 Swedish krona per sensor by switching the LED to a cheaper one, which is nice. And it might sound ridiculous to like save 1 Swedish krona here and there, but every krona that you save ends up being 5, more or less, on the end price. And if you're going to churn out a couple of millions of these, then it's a lot of money that you can spend doing more fun things. So how does it look? This is the BOM cost estimate, roughly, where the costs are. I thought someone might be interested. A jack is really expensive, especially if you need something that is waterproof, which you need if you're going to do automatic coating. Otherwise, it would be bad. And that's, you see, like 30% of our cost is the jack. And finding a waterproof 3.5 millimeter TRS jack was harder than I thought. There are apparently not that many manufacturers. Fortunately, there's always Shenzhen, and they have everything. The PCB is, oh, can I go on, or? Yeah, good. The PCB is a fairly big cost as well. I would have guessed the MCU was the biggest cost, but not. The temp sensors are fairly costly. The FETs are part of the daisy chain, so that is not something for the sensor. But this is roughly how the cost estimate is on the BOM cost. So what if you want to use these sensors? You can't buy them now, but we will happily sell them to you. Even if you don't want the rest of the system, you just want the sensors to play with, you will be able to buy them. We talk I2C over a very simple protocol that we will of course open up, and with also all the electrical specifications that you need, so you can use it with a Raspberry or something. Don't use the Raspberry, it's no crap. And the problem is you get like raw data from them, so you need to convert that to something. But we'll give you all the formulas for converting the raw data to something reasonable. And then how reasonable, it depends on how much you want to implement. You need a standard TRS jack on the other side, or you build an adapter. It's not that difficult. So let's have a little, does this show? This is just a, no? How do you play this? Oh, that. So this is really fast forward. So here we just show how the soil moisture sensor work, and it samples like a volume of surrounding the sensor, which is why it works to put it in a bit into water glass. And that's fast forward. That's my hot air solder. It's not going to melt yet. But there it got a bit hot for my hand, so I had to stop it. Oh, and then I skipped the light sensor. Or did you see that? Oh, it was really fast. Okay, thank you. Any questions? And as usual, I'm terrible at holding times.
Let's take a few questions.
Yeah.
You mentioned soil types, or a normal soil.
Yeah.
Do you calibrate with a specific soil or soils?
We will calibrate with. Sorry. The question was, what's our definition of a normal soil? And we will calibrate it depending on the soil. Our normal soil is the stuff you buy at ICA. Basically, that's the definition of normal soil. But you will be able, in our system, you will be able to select what kind of soil you have, and we will have different properties for it, so we will adjust the values. But the sensors themselves are extremely stupid. They don't know anything. They just give us the raw values, and then we do all the processing on the controller. They do contain calibration data when we calibrate them, so it doesn't. So the calibration data for the temp sensor and stuff is stored in the sensor, but you can read that out as well. Yeah. Was that answer to your question?
I just wondered if you're outside of Sweden and you don't go to ICA and you've got.
Oh, you go to Tesco and then you pick up there. So.
I mean, not just Tesco, the soil types can vary so much depending on the plant. So.
Yeah, but it doesn't affect that much. Soil is basically still soil, and the.
Well, there's a difference between clay and hot soil.
Yeah, but clay is not the normal kind of soil that you put in your plants. Clay soil you normally use when you are a farmer and you use it on the fields. But no, this is not designed for that kind of use. So it's designed for greenhouse where you have normal cultivation soil, which is the kind you pick up at ICA and stuff. But we will of course be able, if you have a clay soil sample, we will be happy to adjust for that as well. Yeah. Yes.
I think it's cool what you've done. I think the cost great. My question is, did you really need to do all of the cost reductions now? Couldn't people afford 50 krona or 100 krona?
Actually, the question was the cost reduction to do now? And the answer is yes. Because we showed this at Garden Fair last year, at the Hemovilla Fair, and we spoke to a lot of people, and the price point is fairly set. So people are not willing to pay more than like 150 Swedish for a sensor, for a wired one, and they're not willing to pay more than 350 for a wireless sensor. If you need many, of course, there's the Parrot Flower Power, which sells for 600. But you normally just you buy one of those and have in your like favorite plant indoors. But if you want multiple sensors, which is what our system is designed for, then the magic number is around 150 for wired ones and 350 for wireless ones. So yeah, we had to turn every single crowd around. Yes.
The capacitive measurements, could you measure soil salinity, salt in the soil? With that?
The question is, can you measure the soil salinity and stuff? pH and stuff? No. They say you can do it using measuring the electric conductivity, which is the resistance based, but it doesn't really work really well because there's so many factors that affect it. So it's more or less qualified guesswork. If you want to buy a professional grade pH meter, they are really expensive, and they have some kind of porous medium that ions walk through, and yeah, then you're away from the consumer grade hardware stuff. Sorry?
Most of them don't last that long.
No, and right, and they cost the cheaper ones are like 500 Swedish, I think, and then they go up and up and up depending on. Yeah, and a lot of the cost is actually the calibration of the pH sensor meeting. So it has to be recalibrated every once in a while, and you have to do it with distilled water and stuff. Yeah. Let's see. Yes, over there in blue.
Is there any foreseeable way to detect diseases or insects using motion sensors?
Okay, so the question is, can you detect diseases or stuff like that using moisture sensor? The answer is no, but there are other ways to do it. So if you take a normal camera, so the simple way, if you take a normal camera and then you remove the IR filter, and then you film your plant, and then you run it through an algorithm, I think it's called the NVI or NDVI or something, which is basically how NASA takes a look on the Earth. They have a camera in space looking. And from that, you can determine whether the plant is healthy or if it needs some kind of nutrients or if it has animals, pesticides on it. But yeah, we're looking at that as well.
Can you use UV light as well?
Probably not, no. Was that answer enough? Okay, good.
What's the battery life?
The battery lifetime for the wireless sensor, that is unknown. Mostly because we haven't decided what kind of battery it is. But the wireless one will have a small solar cell that will recharge the battery. So it will probably not be a problem. The wireless ones themselves, we use a 2.4 gigahertz radio on using 802.15.4 networking radio, so a small protocol about that. We spend most of our time in sleep mode, where we draw basically nothing. The radio itself that we use an Atmel R21, which is the ARM core combined with their RF233 radio. It draws about 15 milliamps in active mode, which is not much, but since we're only alive like 1/1000% of every second, it has very low power usage. And we do automatic meshing and we do self-healing. So the range is about 50 meters in free line of sight and about 10 meters indoors through normal stud walls. Oh, so I ran over 10 minutes. I hope it's okay. Right. Which is, but it's not on all the time. Yeah. So should we end there?
Yeah.
Okay.
Good job.
So apparently I have to end. Thank you. If you have any more questions, just grab me in the break and I will happily answer them.